So over here, I'm just going to talk about what I currently have done so far from last time. Last time I left off at differential calculus and talking about actually, I didn't even talk about this. So here we have all of the matrices, all of it just memorized. Linear algebra is just memorization, in all honesty. There's nothing really to test on. That's why they keep on giving you true and false questions, because there's literally nothing to test on that's practical. I mean, it's all practical, but there's too much like properties and blah 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 blah. So basically it's very basic if you look at it objectively, it's just memorization. And all the important part is just memorization. All the not important part is the, not memorization part. Anyways. So, but most of this is already given to you. I think most of them we already did before. So it's just reviewing all the rank is the first thing that's new, but that's the reason I gave you like one question. And in reality, the only reason I use this for is the Buckingham Pi theorem and getting the rank over here is is there. But that's it. Over here, neutrality is just never used. I have never used this stuff yet, which is why I don't really explain too much about it, and I just show you how to get one question down. But I've never used neutrality yet. I think it's gonna change because I'm about to take a numerical linear algebra class, but for now, it's there. And then we just go the diagonal one definitely used a lot. Identity definitely used a lot. I guess I used it. This one never have used because we after you're getting this format over here, you just plug into a calculator and you're done. Maybe I should reformat this. Anyway, triangle matrix, yes, I have used that. Upper triangle have used that too. So there you go. Why? It's just a memorization at this point. You can identify it as like a ABCD question on like which one you choose. I told you linear algebra currently, as I know it, doesn't have a lot of have a lot of problems. It's just memorization. But my knowledge of MAE 18, Math 18 is all just memorization. Math 18, I just have to memorize all the stuff. That's it, which is why I didn't like it, but it was a fun class to do. Let's just say that. Um, yeah, that's why I'm adding it with the differential calculus. Anyways, we move on to here. We do a slope field, a courtesy of my university giving me a code for that. Anyways, I just do a few of them, and then I realized after doing this stuff, man, this feels very impractical by just doing it. That's why I decided I need to do a practical question. So the first main thing I did was the salt mixture ODE because this one is I already did a long time ago. So it was like, there you go, I have it here. Um, yeah, and you can pause and check as usual. My textbook is in the description below. And then we go to Newton's law of cooling over here. As you can see, K is constant for a certain material. That's how I got this question to run. Very long question, I must say. And then we do a switch question because electricity, electrical engineers is like one of the core hallmarks of engineering, anyways. So we definitely need to do some. I definitely thought ODE on this one was pretty important, so I decided to do a few of them, just a few basic ones, not anything advanced. Especially since it's one first order, there's nothing advanced I can actually do here. And the fourth order reaction. Basically, this was an AP class question, so there's not much to talk about. Here's a more interesting one, but ultimately, this is only possible because x goes to infinity means that the IC and BC can be combined to a one variable unit. So one variable unit is this over here. No, this one over here. This is the one variable unit. Yeah. So be careful. That's the only reason this is possible. In real life, the question becomes way harder. Yeah, and then you get these kind of question. That's why you need Fourier series and everything. But this is not for this is basic stuff you can do. Anyways, we move on to angular velocity motion, which is just doing this stuff. Uh, I literally just chose this because I knew I could figure out sine over here. I could get sine over here. That's the only reason because I realized I haven't done many of those questions where there's like a sine or cosine or something like that as our omega as our tau over here and the end over here. We haven't done that. We haven't basically this is a inhomogeneous in reality first order question, but there's no reason for me to say that. So I didn't do that part. That's why I decided to do that. Literally, that's the reason why. And then we kept on going to compound interest. This was more like real life situation because there's compound interest is like very clearly obvious something we do, and it's something we learn in AP calculus, so why not? And then over here this is just more. This is the first nonlinear one, the tumor growth. I decided to do the tumor growth because think about it. This is basically a logistic curve and then real life situation, but logistic curves wasn't really that bad. And then we do linear drag where I lose my mind. I literally lose my mind because it was such a painful question to do because it's non-linear. The quadratic drag was like non-linear, so it was a pain. And then we do something simpler with axial deformation, and then we move on to exact. And in exact, we move on to the first electrical charge one over here, where we get where we use method of imaging to get this kind of cool like potential everything. Like it just shows potential. Like you can get potential from over here and put here, and see the potential over here, the difference over here. Now I could have put the electrical field lines like this. I didn't. I could have, I didn't do it. Uh, Mainly because I didn't think of it at the time and I didn't really consider it. But definitely in physics 2B, I will, in the physics section for electrical magnetism, I'll definitely do that. Over here, there's a entropy, that's just a heat transfer. And then we finally went to fluid potential fluidity. Notice that it's very much analogous to electricity. So anything that a fluid mechanics like waveform looks like, uh, the electricity version of it can do the same, literally almost similar things. I must say this came out really good. This is in Python, unfortunately. Um, and yeah, it was okay. It worked out well. Uh, I don't really have any complaints to it, so I don't really know what to tell you guys. This is like the clear visual. Like this is the streamline over here, and probably a river like this big, and this is like a hose going into the thing. That's why I say models of river dam, whatever. Clear all things. Over here is a double, and it has some modeling for finite fluid bodies and a very large anyways, and then electromagnetic. It can be electromagnetic analogy if you change the water source to like a charge, negative positive charge collide together or something. No, I think like a positive, no, negative positive, yeah, collide together. You can make a dipole effect. Either way, you have a visualization. And dipole effect, this is in the fluid mechanics, you use dipoles for one part of it. Basically, you add another part called a free zone, which will make this a sphere. And why a sphere is important is because you can actually transform a sphere into a wing. Now, why is that important? If you can transform it to wing, that's the best analytical solution you can get. I forgot what it's called. It's like a Kulikowski wing or something. I forget. That's the best analytical wing you could possibly get. And then we do utility functions over here. Voskian and rotation matrix. I was gonna do more question on the rotation matrix because space mechanics has a lot of rotation axis as a but I decided against it for now. I might actually go back to it and say, nah, we're doing that. Next, I decided to put all the cases down for a generic second order question. Anyways, we start with just some proofs over here, but I decided to immediately go to like real life example, physical example, which is a linear spring. We use guess over here if you read any of this. I wrote that you guess this because we know that sine, cosine, and sine h and cosine h and a linear line can be used because of Euler's equation with this one thing, which covers like many of these situations. Um, yes, and if they're because it's linear, this works. If it's non-linear, then this, yeah, it becomes a pain in the ass, and you're gonna have to do a lot of pain to figure things out. Um, Now we finally bring into a real spring question over here. Now we definitely I definitely should realize that this T appears out of nowhere, which I didn't really prove anywhere. So here I just proved it real quick. It's not bad. I also made a mistake here. There's supposed to be a minus here, and I put a plus there for some reason. I remember that because I was there for a long time, and I realized it way later. If there's a mistake in my textbook, please email me, please text me, please comment, do anything to get my attention. Anyways. First one interesting because sign H. I really wanted to bring one that was sign H because it really brings in the flavor that it can actually get hyperbolic functions. But in reality, I'd rather have myself submit this because this is more understandable to me. This makes no sense to me. This doesn't really have any sense to me, and I should have probably boxed in this more carefully. Actually, thinking about it, that's correct. I should probably box that more because, in my opinion, it makes more sense for me mathematically and logically to have this as our solution. This solution makes more sense to me than the sine H solution, although I gave that solution out. We do a few more of these for the different cases, and then we move on to electricity with the voltage. With the charge, this is a charge question. I only did one of these questions. The reason why is who the hell cares about charges in engineering? I've never seen a person say, let's go find a charge of electrical circuit. I've never seen someone do that. So I don't think it was that important. So we did one question about that and moved on because it's why. And then we move on to these two situations over here. But this case is I realized that it's like you need to know the I initial and then so you basically need to know this. And I was saying at that point, if you have these values like 5 or 6, uh, you kind of, or you probably already have the whole graph already. So what's the point of it? So I realized then that I was thinking, well, I mean, you can at that point just use numerical because you already have the data set basically. Instead, I decided to make a more convoluted question where you basically switch off this thing and you have to figure that out, and you finally get this kind of like ooh pulsation, which I was saying man, I chose values that were insane or something, which yeah, that was fine. Anyways, we do ideal pendulum next. This is the first. I realized in the spring when I skipped over this one where we actually solved this. If you solve it, it was boring. That's why I didn't really explain much. But you basically get oscillation like this and constant weight like that. So it's not really that big of a deal that you missed that. Anyway, we finally get to the pension. Now, inverted pension, why did I choose the 15 one? Because in control, this ODE is actually valid and the one that you would use to, because your control box over here will control this to go this way. And then if it goes over here, it'll go that way, making it basically 15 degrees at max or something. The only time it does, and then that's why this second one is useless usually and the le less valuable, even though it shows more. It shows from 0 to 360, but and then it shows basically a crash. This over here, I stopped it at pi divided by 2. So basically, this whole thing crashes at pi divided by 2, basically. But the why is not valuable is that this here is the most hard information. Over here, it's basically mostly gravity. This thing is almost like if you look at the sign, it's basically free fall. Like imagine throwing a ball down and just letting it go. It pretty much is that basically, which is why this is not useful because you can basically model. You see how it's linear or something? This looks basically like a kinetic problem where the mass is dropped. Anyway, the reason I did all these questions because we need more negative coefficient. You realize that the mass over here and the pendulum over here, it's all positive coefficient, and if you move all the things to one side, positive, right? And then you can't really change that. The only way I can change that because I need an unstable system that explodes, and that explosion is very hard to come by in traditional mechanics. So we had to bring this up, and then the other thing I have is a active dampener that I think I will do later, but not right now. We're waiting for my brain to actually work, and because I think I need to move on to a non-homogeneous one, which is going to be a pain because look, I mean, it's pretty much a pain. Um, yeah, but a lot of times we're going to deal with positive numbers just because a lot of the real world examples I found has just positive, positive, positive. So we're going to deal with a lot more positive than negative, and then we might deal with impulse, which will allow us to do basically this. This is our Laplacian to solve question, which will allow us to do impulses and probably some control ODEs, which means I can bring in negative a little bit. I'm not done with this part. I'm definitely not done. It looks ugly as hell, and I don't have a physical example yet. So yeah, we're still stuck here. I just finished this. Anyways, I'm gonna stop recording. That was it.